Greetings everyone. We are Team 9 or also known as Q Engineering. Our team consists of me, Adila, Pang Kang Ying, Zulfadli, Nurul Najiha and Siti Hajar. In this presentation, we will explain on our overall process flow diagram, mass and energy balance, simulation, deviation and waste management. Let's start on the process overview. Our team targets to produce acrylic acid as our main product with propylene and air as raw material. The byproduct generated is acetic acid. After much discussions, the process synthesis route chosen is the two-step oxidation of propylene. From our previous market survey, acrylic acid is seen to have high market demand, especially in the Southeast Asia. This is due to the various applications of acrylic acid, such as the production of super-absorbent polymers, surface coatings, adhesives, and many other industries. We have also decided to locate our production plant in Rayong, Thailand, as it benefits our company in many factors. Now, let's go to our process flow diagram. In the production of acrylic acid, we have designed a process where 5 major unit operations and 2 minor unit operation is used. The process starts with air, steam, and propylene as our feedstock. Firstly, a multi-stage compressor system where 2 compressors with an intercooler in between is used to increase the pressure of air. The pressure of our raw material propylene will be reduced using a pressure-reducing valve. Then, all the feed stream in vapor phase is mixed and then heated before entering the fluidized bed reactor. The reaction produces acrylic acid as main product and acetic acid as byproduct, and also off-gases such as carbon dioxide and unreacted propylene. As the vapor mixture exits the fluidized bed reactor, the pressure is reduced by pressure-reducing valve and cooled down before it undergoes liquid-vapor separation by the flash column. The off-gases are removed from the liquid mixture of acrylic acid, acetic acid, and water. The liquid mixture then enters extraction column where water is extracted out from acrylic acid and acetic acid mixture. We are using diisopropyl ether as solvent. From here, water is largely removed. The outlet stream consists of acrylic acid, acetic acid, and solvent diisopropyl ether. Then, this mixture enters the first distillation column, where diisopropyl ether is distilled at the top stream. Meanwhile, the bottom stream consists of our main product, acrylic acid, and byproduct, acetic acid. Finally, this binary mixture is separated at our second distillation column, where acetic acid exits at the top stream and acrylic acid as our main product is obtained from the bottom stream. So going back to the flash column where off-gases and other impurities exit from the top of flash column, then the stream enters the membrane separator where off-gas exits at the top stream and wastewater exit at the bottom stream, which will both be further treated. Furthermore, as a proactive step for the sustainability of our process, we have designed a recycled stream for the diisopropyl ether. This is possible by adding a gravitational decanter to separate the diisopropyl ether from the water mixture and reuse it as a solvent in the extraction column. This is the first part of our stream table. S6 is our main feed inlet where propylene is fed at 85,000 kilograms per hour. Next, the two-step oxidation reaction occurs in our fluidized bed reactor, which produces 1,912 kilomole per hour of acrylic acid and 38 kilomole per hour of byproduct acetic acid. Then at the second distillation column, our main product stream, S23, has the mass flow rate of 134,404 kg per hour with 1,863 kmol per hour of high purity acrylic acid.
For mass balance, the assumption is that the system at steady state, no leakage at pipeline and vessel in the system. All components are behaving at ideal condition and total input-output similar for all components passing through compressor, pump, valve, mixer and heat exchanger. So next slide, this is our front part of PFD. As you can see from the diagram, there are 3 feedstock inlets supplied to the fluidized bed reactor. The first stream show about multi-compression system for compressed air. According to heuristic 35 and 36, the number of stages should be 2 as our final desired pressure is 6 bar. So, first stage we compress to 2.45 bar and second stage to 6 bar. By using the formula shown, we can estimate the final temperature rise at the outlet of each compressor. So an intercooler here is introduced to reduce the temperature change back to 25 degrees C for second compression to occur. So for the reactor, the chemical reaction acrylic acid synthesis, acetic acid synthesis, carbon dioxide reaction at the conversion as stated. The operating condition for FBR is 6 bar and 175 degrees C. So next, this is the basis assumed. As you can see from the table, the inlet and outlet mass for our flue gas bed reactor is balanced, and the mole are being calculated by the extent of reaction. As there are 3 chemical reaction in our plant, so they have a 3 epsilon as well. So after the mixture comes out from the outlet of fibrillous bed reactor, the mixture reduced by the pressure release valve from 6 to 1 bar and cool down to 47 degrees C by a heat exchanger. So next slide. The mixture enter the flash column. The assumption for the flash column is as stated, with the light key component 0.99 and heavy key component 0.01. So, for the separation concept in flash column are based on the boiling point difference. The vapor phase component like nitrogen, oxygen, carbon dioxide and propylene will exit at the top and enter the membrane separator for further separation, while the bottom consists of acrylic acid, acetic acid and water. For your information, the feed temperature for our flash column is 47 degrees C and assumed in between boiling of high key and low key component. So next slide. This is our membrane separator. A pre-evaporation process will be used to separate the off gas like carbon dioxide, nitrogen, oxygen and aerated propylene from the wastewater. The operating conditions are at 1 bar and 30 degrees C. Assumption for this unit operation are continuous process, steady state and no side reaction occur, and the efficiency of the column up to 99.99%.
So now I will be presenting about the extraction column. In our process, the extraction column uses diisopropyl ether as solvent to perform liquid-liquid extraction to extract out the alkalic acid and acetic acid from water. Hence, the raffinate phase consists of mainly water. In our case, some of the assumption has been made. First, the liquid-liquid extraction column operate in 1 bar and 47 degrees C, as the feed temperature are in 47 degrees C as well. And then, the column consists of 6 stages, as feed enter from the first stage, while the solvent enter from the last stage. The extraction process are in counter current flow, as the extract will exit from the top and raffinate exit at the bottom. The mass balance of the extraction column are determined by using the ternary diagram of the diisopropyl ether, alkalic acid and water in equilibrium, while the number of stages are using the Kramser equation. After obtaining the mass balance from the ternary diagram, the extraction factor and distribution coefficient are calculated using the mole balance data and substituted into the Kramser equation. As you can see from the table, the operating pressure is 1 bar for all streams, while the temperature are varies because there are 6 number of stages. Furthermore, the mass are also balanced, as the feed inlet stream 14 and solvent inlet stream 17 are equal to extract stream 18 and raffinate stream 19. Next, in this part consists of 3 major unit operations that are vacuum distillation column T1004 and T1005 and a decanter V1001. Both distillation columns are set to 0.3 bar and 99.99 efficiency. For the T1004, the feed temperature will be 47 degrees Celsius, and light key is water with coefficient of 0.99, whereas heavy key is acetic acid with coefficient of 0.01. According to our manual calculation, the number of stages needed by T1004 is 27 stages, with 32.8 degrees Celsius of dew point temperature and 102 degrees Celsius of bubble point temperature. The bottom of T1004 will enter T1005 as feed, so the temperature are same. In the distillation column, the light key is acetic acid and heavy key is alkalic acid. The number of stages needed by T1005 is 25, with 52.3 degrees Celsius of dew point temperature and 105.7 degrees Celsius of bubble point temperature. For the distillation column calculation, step 1 is to determine the vapor pressure for each component. Then, the relative volatility calculate based on vapor pressure will be used in step 2 to find out the split fraction. Next, in step 3, the bottom and distillate component are find out using the split fraction. In this stage, the mass balance are done for the distillation column. For the step 4 to 7, the formulation are used to calculate the number of stages, feed plate location, bubble point, and dew point. Next, the energy balance are calculated based on the first law of thermodynamics. The assumption made for our calculation are reference temperature and pressure are 25 degrees C and 1 atm respectively. The system is at steady state and all the components are behaving at ideal condition. Heat capacity of each component is only function of temperature. Heat of formation of each component is referred to its phase at reference state. Pressure-based enthalpy change are neglected. There are two types of energy balance calculation. One is with phase change and the another is without phase change. First, the heat capacity will be calculated according to the reference state phase. Then, for the total enthalpy without phase change, will sum up with the heat of formation. While for the total enthalpy with phase change, the heat capacity of liquid phase will be calculated from the reference state temperature to boiling point and sum up with heat of vaporization at boiling point, heat of formation, and lastly is the heat capacity of vapor phase from boiling point to desired temperature.
We have used Aspen Plus to run our process simulation. As you can see from the slide, we have used this basis to run our simulation. The basis is property method of NRTL. Flow basis for input is by using mole. Method filter use is common method. Input mode is steady state and ambient pressure is 1 bar. The method used for each unit operator has been listed out in the slide. After the simulation has been completed, the value for energy and mass flow will be collected and tabulated in the Excel for comparison purposes. To calculate the deviation, the equation on the slide will be used. This is the flow diagram obtained from our simulation. This is the comparison between our manual calculation and simulation result. On the left is the comparison between mass balance, and on the right is the comparison between energy balance. Our energy balance for stream 1 and stream 3 has a deviation of 100%. This is because our manual calculation uses 25 degrees Celsius as the reference temperature, and the input temperature for both streams has been set to 25 degrees Celsius as well. Since there is no temperature changes, the resulting heat of enthalpy is equal to 0. Furthermore, stream 1 and stream 3 contain only oxygen and nitrogen, and both of the components has a heat of formation of 0. Hence, the calculated value for our energy balance is equal to 0 for stream 1 and stream 3. However, the value obtained from our simulation is not 0, and this has caused the deviation. Our simulation may have used a different form of calculation, hence the difference in the result obtained. For stream 2 and 4, the estimated outlet temperature of the compressor is about 112 degrees Celsius, which is based on heuristic 36. But the temperature obtained from our simulation is around 144 degrees Celsius. The difference in outlet temperature has caused the deviation to be at 37%. This is the waste management practice and legislation. The best practice for waste management will be to reduce or avoid any waste, and waste disposal is the least preferred practice. The Environmental Quality Act 1974 is the most comprehensive piece of legislation promulgated to deal with environmental protection and pollution control. The Act also forms the basic instrument to achieve the objective of the policy. Here is the list of waste components from our plant. The chemical listed out is hazardous to the environment. For our catalyst, the molybdenum component is considered harmful and must be treated. Our wastewater contain high amount of water and low amount of diazotopyl ether, except for stream 27, which is opposite.
For our gas waste management, we are using common carbon capture and storage technology CCS for post-combustion carbon capture. Here we deduce three types of common CCS technology, which are amine-based scrubbing, polymeric membrane separation, and cryogenic distillation. As you can see, we done a weightage score for each of the technologies here. First, we compare the percentage removal and purity. Cryogenic has the highest percentage of CO2 removal and highest purity as well compared to amine and polymeric membrane. In comparison with cryogenic and amine scrubbing, cryogenic is the energy intensive one here since this method using an extremely low temperature and high pressure distillation. Same goes with amine scrubbing. It is simple process by addition of solvents to have high selectivity towards carbon dioxide. However, there is the absorption process for solvent having high capital investment since massive energy required to regenerate the solvent. After consider the three technologies, weightage showed all three having the same score since several factors being considered. So justification can be made whereby using polymeric membrane, a low-cost membrane technology can be further advanced to meet high purity almost same like amines. Membrane can have high yield of percentage removal by adding two stages membrane system and air sweeper technology. Why? Majorly because of the driving force for the membrane separator will be the pressure difference. If we only use one stage, it will first need to compress the feed stream pressure almost 2 to 10 bar and permeate pressure at 0.2 bar to attain the different permeate to feed pressure ratios. This large pressure ratio is an energy-intensive process and increase overall energy penalty. So, to have the pressure ratio difference but in a lower energy penalty, improvement by two stages air sweeper will be recommended because inlet pressure feed designed at much lower pressure of 2 bar. In addition of air sweeper with recycling into the feed, it will increase the inlet concentration of carbon dioxide since portion of carbon dioxide from first permit being recycled. Using boiler combustion air as a sweep gas may remarkably increase the feed carbon dioxide partial pressure and reduce the energy penalty. For unrelated propylene, basically it is an unsaturated hydrocarbon that may harm the environment by forming ozone in the atmosphere. Therefore, disposal of the chemical to environment should be considered. There are many treatments can be used to control hydrocarbon compounds before release. The common one is thermal degradation, which is chemical method and biological method. As shown here, for catalytic oxidation, it is using catalysts and thermal incinerators are the type of combustible ways to degrade unsaturated propylene. Here favors more to catalytic oxidation since the running operation run at a lower temperature compared to thermal incinerator. However, both of these technology converts the unreacted propylene into carbon dioxide and water at higher amount. So, we have one alternative ways, which is biofiltration. Here, removal efficiency more than 90% can be achieved. Biofiltration using ambient temperature and pressure with minimal carbon dioxide release, and usually temperature of 50 degrees Celsius to 100 degrees Celsius is the optimal range needed. In terms of cost, biofiltration did not use any chemical handling that need to store and handle, and no combustion source are needed. For liquid waste management, the three technologies are proposed due to the conventional uses in industry in removing solvent. We have the biological treatment, which are anaerobic membrane bioreactor and fluidized bed biofilm reactor. Another method is physiochemical method, which is supercritical water oxidation, which is conventional method to treat wastewater in acrylic acid production. According to the weightage, supercritical water oxidation has the highest cost in it have the highest efficiency and moderate cost and energy requirement. For solid waste management, we have chosen technology to recover the metal from the catalyst, which is selectively to molybdenum to prevent the metal release to atmosphere. We have suggested metallurgy technology which extract the valuable metal. Example of the method is pyrometallurgy and hydrometallurgy. Another method must be the least preferred but the safe way to handle the catalyst waste properly, which is scheduled waste. According to the weightage, scheduled waste have been the highest score due to highest removal efficiency and no cost and energy needed for this technology. Therefore, we have selected scheduled waste.